Hello everybody, welcome to the latest edition of the Physics Corner, a series of videos in which we set up and solve introductory physics problems. I'm your host, Dr. Christopher Sorolla. Today we're taking a look at work, or more specifically, our real goal is to take a look at something called a scalar product and how it's applied in physics. So, let's imagine we have the following. Suppose you're a shopper at a grocery store and you've got your cart loaded, and you have to push your cart, of course, across an even floor. For simplicity, we'll assume that the floor has no bumps or wriggles, it's perfectly smooth and, importantly, horizontal, right? And you're needing to push your cart down a straight distance of some 20 meters. In order to keep the cart moving at a constant speed, you're traveling at, or you're exerting, 100 newtons of force. Okay, so we've got all that kind of in the background. Here's the question: what is the work done to the cart after pushing with this force, traveling that distance, and having an angle between the displacement and the force of either 0 degrees, 90 degrees, or 45 degrees? And how do you go about calculating such things? Okay, so first off, we're going to need the formula for work. Now, work is a scalar quantity. What does that mean? That means that it is a quantity that only has an amount. Now, work could be positive or negative. It's possible to have it that way, but there's no directionality associated with work. On the other hand, to get to this, we do need to consider quantities that have vector, that have directionalities. That is a force and a displacement. And so work is equal to force dotted into displacement. Now, what exactly does that mean? I'm going to talk about that in just a moment. Now, the formula to calculate that, to find the amount of that, turns out to be this little gem right there. Okay, so what exactly are we discussing? Well, first of all, I'm going to go through the problem a little bit. I'll do an example of it, and then we'll come back around and talk about what we've done and why. Okay, so let's use this part here first, all right? So now, we won't need to draw a free body diagram so much because we're not really interested in solving for forces, but it might help to draw a diagram of some kind. Okay, so let's imagine we have something very much like a cart here. I'll just draw a very, very small version of a cart, and we're going to exert a force to push it a certain distance. I'll say it's 20 meters, of course, right? Which I'm going to label delta x like this, all right? Now, the question comes in, what is the direction of the force when we do this? Now, to make this very clear, let's have our displacement specifically as a vector that starts from the cart here and goes to the cart over here. So there's our 20 meters. Let's just say forward to our direction. That's going to be fine. All right. But then we have to consider what is the direction of the force. Now, the force can either be a force like this, which is exactly in the same direction as the displacement. That would be question A, 0 degrees. We could have a force that is, say, either straight up or straight down. I'll say straight up, just to give it a direction. Looks like that. That would be force B, if you will, direction there. So that's the 90 degrees. And probably more realistically, a force that's something like this, which is tilted at a 45-degree angle to our cart like that. That'll be our 45-degree angle, which is question C. So those are our three answers now, or three cases. Now, let's solve for the first case and then talk a little bit about why it works that way. So, in case A, the work, I'll just give it a label WA to distinguish it from the work that we're going to discuss for the other cases. But the work then is equal to force multiplied by displacement, or distance that I displace, and then cosine of the angle between those, like that. So, 100 newtons, 20 meters, and cosine of 0 degrees. Now, if you remember your trig a little bit, cosine of 0 degrees is exactly equal to 1. 100 times 20 is 2,000, and my answer is very simply 2,000 joules. Notice that there's not a direction associated with this, okay? It's just simply a number because it's a scalar. Okay. So let's backtrack a little bit before we get to doing the other questions. What is all this specifically, and why are we doing this? Well, if you want to multiply two vectors together, you have two choices as to what kind of result you're going to get out of that. One is you can multiply the vectors together in such a way that you get a scalar, just a number without any directionality, or you could multiply the vectors in such a manner as to come up with another vector, okay, which does, of course, have a direction. This particular case, we're doing a scalar multiplication, or as it's called in the business, a scalar product. Just a word we've stolen from mathematics. Product is just another word for multiplication for our purposes here. And so, scalar product, or sometimes called a dot product, because of the big thick dot that's right there, that is what we're trying to accomplish with this particular example. Work is a scalar quantity. We don't want a direction associated with this. So we're multiplying two vectors together, getting rid of the vector nature, and coming up with a scalar, or just an amount of something. Now, how do we resolve the vector issue, or how do we deal with the vectors, the directions they're pointing in? Basically, a way to think of scalar product is that it's taking two vectors and asking how much in common do they have in terms of direction. If they're pointing in the same direction, which is exactly 0 degrees, then you get the maximum possible scalar product. If they are in opposite directions, perfectly opposite each other, so say the force is to the left and the displacement was to the right, for example, then that would give you a 180 degree angle, and that would be a negative. You'd still get a maximum amount of magnitude, but it'd be a negative sign on that. And if you have the vectors with nothing in common in terms of direction, and notice how I'm phrasing this, if you're in opposite directions, it's not the same thing as saying you have nothing in common. If you're in the opposite direction, you're along the same line, if you will, going along the same dimension or coordinate. To have a vector or pair of vectors have nothing in common with each other, then they must be at right angles to each other. Something like these two vectors are drawn right there, for example. Now, you might recall that this came up way back when you just talked about things like, say, two-dimensional motion, and how the coordinates were independent of each other, right? Still the same talk here. Still means the same thing. But if they're independent, that means they have nothing to do with each other. So, what does that imply? That implies that if you multiply two vectors together, they're at right angles to each other, the result is nothing. You get no commonality, therefore nothing results of it, right? Which is to say, let's do the second part to show that off. Let's suppose I ask for the work done if you try to push the cart forward. But let's think about this physically as well as, say, in terms of math. The displacement I'm trying to achieve is in this direction, but I'm taking the cart and I'm pushing it straight up. Whatever else happens, even if the cart does go this way for some other reason that's not, say, specified, I'm not really doing anything to make that happen, am I? And so if I write this out carefully, we still have 100 newtons of force that's being directed. The cart might still travel at 20 meters. The cosine of 90 degrees is 0. And so no work is done. Okay, so here's the physics interpretation of it then, if you will. To have work done to an object, you must have at least something in common between the direction of the force that's exerted on the object and the displacement direction. Okay, they have to have something in common. They don't have to be exactly in the same direction, but they might at least have to be pointed somewhat in the same direction. Let's say, in other words, have components in the same direction, if we use that kind of speak. If you have two vectors that are right angles to each other, they're independent, which means direction-wise they have nothing to do with each other. So that's what happens. All right. So this dot product is an expression. That's the mathematical symbol for this process. Take two vectors, combine them together, or multiply them together in such a way as to produce a scalar. So scalar, or dot product as it's called, and that's what happens. This is the way to calculate the magnitude of that. Now, why cosine? Well, let's take a look at what cosine does. Cosine of 0 degrees, which is perfectly along the same direction, gives you 1. Doesn't change anything. In fact, you get the maximum because that's the largest that cosine can ever be, right, is the number 1. If they're in perfectly opposite directions, cosine is, the angle is 180 degrees. Cosine of 180 degrees is -1. So you get the maximum amount, but in the opposite sense. So that's why that works that way. And cosine of 90 degrees is 0. which is again a statement of how much in common two vectors have with each other. If they're at right angles to each other, direction-wise, they have nothing in common. They're independent of each other. Okay. So let's do the last one. Now, I saved this one for last partly because this is a far more realistic approach to actually pushing a grocery cart. So if you take a look at a picture like this, here's a grocery cart, and you've got a handle here. Most of us, I won't say everybody, but most of us are taller than the grocery cart. You're reaching down to push a grocery cart, right? And there's a good chance you're pushing downwards at an angle of about 45 degrees, aren't you? Okay? So there's an angle here of some 45 degrees compared to, say, pushing the cart forward. So this is a more realistic approach, if you will. I am, of course, as usual with a lot of our physics problems, we're kind of shading a few details here just to get across the main point. So let's not get too worried about the super fine details. Let's run with what we've got. But what does that mean? That means then we still have 100 newtons worth of force that you're exerting on the cart. The cart is still traveling forward 20 meters, but now the cosine is of 45 degrees. Now, to write this out a little more carefully, you can check this with your calculators, of course. Cosine of 45 degrees is, if you prefer, the square root of 2 divided by 2, or 0.7071 if I round off a little bit. And I'll round off for my answer to the nearest second significant digit, and I come up with a total of 1,400 joules, like that. So that would be how that works out, which is to say, some of the effort you're putting into this, and by the way, effort is not a physics term, but some of the effort you're putting into or exerting on the cart isn't going into moving the cart forward, right? You're not delivering all that you could. Now, the reason we do this, of course, is like I said before, most of us are taller than the cart itself, and it's just a lot more natural, it's a lot more comfortable to push straight down. You could, in theory, crouch yourself way down to push the cart perfectly forward, but that's very awkward, and that's kind of, that's not really helping you. It might help the cart, but it's not helping you, so we don't tend to do that. Major lesson, though, is this. There's something called a scalar or dot product. It is a way to multiply vectors together to come up with a scalar as a result. And this shows you examples of how that might play out. Okay. Technical assistance for these videos is from Sydney Gautraw and Sophia Turner. Funding comes from the University of Mississippi and University of Southern Mississippi. We make these videos in Hattiesburg, Mississippi. I am your host, Dr. Christopher Sorolla. Thank you for your attention, as always, and clear skies.